So if you're interested in how you did on the first homework, we have the results right here, anonymized, just for fun. So here are all the teams. So the horizontal axis is your team number, including the GSIs and including the optimized BLAs, and including the naive code over here. And the vertical axis, I'm sorry this doesn't fit very well on the screen, is percent of peak. So you can see, and there are three curves because one of the curve is the max, one is the median, one is the average performance over all the test matrices. So you can see that if you take the absolute optimized code by the vendor, we're getting over 90%, and everybody else got some fraction of that. You know, and these are all sorted by, let's see, average performance, yes. So, and then the naive code was here, and then the block code was actually not much better, and I think that's because the test problem was so small it fit in L3. We should have given you a bigger test problem. And then here are all the other ones. So some years it's unusual, but the let's see how the GSIs did. There's Team GSI. Let's see, but they weren't the best. So somebody out there beat the GSIs. So good for you. So. And assignment 2 is out there, right? And all this is on the class web page, so you can go take a look at it at your leisure. So let's go back to the lecture. And so we're going to have 2 lectures, today and Thursday, on the dense linear algebra motif, or dwarf. And as time marches on through the semester, we're going to be walking through several of the dwarfs to talk about how to optimize them in the best possible way, what are optimal algorithms. But let's start with a very quick review of an earlier lecture. And so here's a question, a quiz question. What do you call a program which is written in PyGas? Now that's one of the languages that Kathy Yellick talked about. It's a global address space language based on Python. And this program uses a Monte Carlo simulation algorithm to approximate pi. And it has a funny race condition, so that it gives you a different funny answer every time you run it. So what is the name of this program? Any guesses? Monty Python, right? So yeah, you have to like bad puns, so that's an important thing. Okay, so that's a review of the previous lecture. And so now let's go on to today's outline. And so I'm going to give you a little history and motivation, and give you the lower bound on communication, which applies to every algorithm in this particular motif. So as I've said before, you know, communication is where all the time and energy goes, and now we know how little we can get away with, and I'll remind you of that. Then I'll tell you what is in this motif, because most of the time these routines have been well optimized before. They're existing libraries that have been provided by the vendors. The vendors just don't do matrix multiply by itself. They build a whole hierarchy of stuff on top of it. Now, it turns out that none of these libraries yet attain the lower bounds, because these are too recent, and the algorithms that attain them are too recent, so there's lots of ongoing work, including possible class projects, to implement some of these new algorithms which actually do attain the lower bounds. And then I'll dive into matrix multiply again, but now in the parallel case. I'll tell you what the lower bound is, and I'll tell you some of the new algorithms that have only been discovered recently that do attain these lower bounds. And next time, I will repeat the story for Gaussian elimination, which is a more complicated algorithm. So anyway, so let's get started with this. And just to put it in the context that we have in this class, which is that there's a certain number of patterns, and here I have the 12 computational patterns that appear over and over again. I'm talking about this one, which is linear algebra on dense matrices. So what is dense linear algebra? It's not just matrix multiply. Most of the time people want to do a higher level operation. And so here's what is usually considered to be in there. Well, solving linear systems, so A/B in MATLAB, that's certainly in there. Many flavors of it, as you'll see. Solving least squares problems, so that's choosing x to minimize the residual, ax minus b. And the typical case is when it's overdetermined. A has more rows than columns, and that's an overdetermined system. But there's also the underdetermined case, in which case there might be many solutions. You still want to do it. And this is the standard case where you have no constraints, but you might have some extra constraints that x has to satisfy an additional underdetermined system of linear equations and minimize this norm. So there's a constrained problem, and sometimes people have weights, that some of these equations are more important than others. All of those are available in these libraries. Eigenvalue problems, so both the standard one, ax equals lambda x, and the generalized one, where you have two matrices. That's pretty common in practice because you may have a stiffness matrix and a mass matrix if you're in civil engineering. They both show up, and that gives you the lambda or the frequencies that you want. In addition to the symmetric case, there's the non-symmetric case, which is more complicated because you don't actually always have eigenvectors for every eigenvalue. And so there's a lot more varieties that people ask for. So the eigenvalues themselves, Schur form, which is the closest you can get to diagonalizing a non-symmetric matrix and keep it numerically stable. You can ask for the eigenvectors, and if those may be problematic, so sometimes people ask for the spaces spanned by those eigenvectors, and those are called invariant subspaces. And again, you could have one matrix, or you could have two matrices to define the problem. And these are parts of all these standard libraries. There's something called the singular value decomposition. If you're not familiar with that, don't worry about it. You can think of it as basically the eigenvalue problem for A times A transpose without bothering to write down A times A transpose. And then there's variations in all of these because not all matrices look alike. There's, of course, real matrices and complex matrices, and sometimes the algorithms change significantly. But your matrix may have interesting mathematical properties. It could be symmetric, for sure. I've already mentioned that. If it's complex, it could be either symmetric or Hermitian, which is a different kind of symmetry. It could have another property, which is called positive definiteness. All its eigenvalues are positive. That changes the algorithm to use again. And even though this is called dense linear algebra, it includes not just full dense matrices, it includes triangular matrices, and includes banded matrices, where the band is, can be arbitrary. And all of these are part of this dwarf. And then the users want all sorts of different levels of access. Some of them simply want to type A\B. That's the simplest thing you could do. But there's a lot of interfaces that provide error bounds, because some people want to know, can I trust the answer? They may want some extra precision. They may want to say, I want to know just a subset of the eigenvalues. Please do that more quickly for me. And then there's a whole hierarchy of other routines. All of these are available. I'm only going to give you a hint about matrix multiply in detail about how it works, and then Gaussian elimination next time. But the ability to do optimal algorithms can be done for all of these in principle, even though it hasn't all been pursued yet. So let me give you a little history of how all of this has evolved to the current day. And it goes back a ways. So in the beginning was the do loop, right? So people started doing this a very long time ago. And that was enough to build libraries in the 1960s called IcePack, which was for eigenvalue problems. But that became hard to maintain. People wanted to develop something more general. And I already mentioned this particular development in, I think, my second lecture on matrix multiply. Then people decided to invent something called the BLAS, the basic linear algebra subroutines. And they were invented, a standard set of operations on vectors. So alpha, scalar times x plus a vector, dot products, things like that. And this was the reason people did this is that they were used over and over again, so they figured, why don't we build it once? That way you can hide all the details, how it's optimized for a particular routine. And so the goal was, of course, to ease programming, but it was also to make sure you got the right answer. And these all seem so simple, you could wonder, how could I possibly get the wrong answer? And the simplest example is if you want to compute the 2 norm of a vector, the root sum squares, the obvious algorithm, sum the squares, well, you can get overflows and underflows even though the final answer is perfectly represented. And all those details of how to get the right answer despite that, those are all hidden inside this interface. And so this was called the BLAS1. And that's sort of, historically, why was it called that? Because it does order n to the 1 operations on order n to the 1 data. And of course, we're going to have BLAS2 and BLAS3 in a moment. But this is the BLAS1. And this was used in libraries like LinPack. That was the next library that was built after IcePack. And LinPack was for solving linear systems. And of course, when we think of LinPack today, we think of the LinPack benchmark. So this is where the name comes from. Nobody uses that code anymore because it's very slow. And so today, when you think of LinPack, let me just remind you, it's used to measure the fastest computers in the world. And every 6 months, they all get ranked at supercomputing conferences. So as of the last ranking, which was November in 2012, the fastest machine was this Cray Titan at Oak Ridge. And it was doing Gaussian elimination on dense matrices. That's how they race. And it achieved 17.6 petaflops out of its peak of 27. And that's only because it used all 18,000 NVIDIA cores that come along with all of the 18,000 Opteron 16-core processors. So it kept everything busy all the time to get this large fraction of the peak performance. And sometimes in this database, they also tell you how large the matrices were. They're usually in the size of millions, and it usually takes a good fraction of 24 hours to run the benchmark. But they decided not to tell that particular data, so I can't tell you that. And it's interesting because all of this data goes back in history. You can sort of look at how things evolved over time. And so one of my favorite examples is a Palm Pilot. So they actually ran the impact benchmark on a little handheld device. And of course, they don't do a million by million matrix on a handheld device. It was 100 by 100, which is all they could fit. And it got a whopping, 1.7 kiloflops. But anyway, all that data is there, and you can plot log curves to your heart's content. Okay, so the BLAS1 were obviously not enough. And the metric that we used to explain why they weren't very good was something called the computational intensity. So what I do is I take one of these operations, and I count how many flops, and it's 2n, so it's n multiplies n adds, and I divide by the number, the amount of data that you have to access to do the job. So I have to read x, read y, and write y, so that's 3n reads and writes, and that's 2/3. I'm only doing 2/3 of a floating point operation per memory reference. And since memory costs so much more per operation than doing the arithmetic, this is going to run nowhere near peak machine speed. And so that wasn't good enough. And so the next level, when people tried to optimize this, they moved from the BLAS1 to the BLAS2. And that was another library where they added higher level routines. And it's basically matrix vector operations. So the most common one is general matrix vector multiply. That's the abbreviation for it. So a matrix times a vector, and then you have a scalar times that, and you can add it to a scalar times this. So why do you have this combination? Because that's exactly the inner loop of Gaussian elimination. You're multiplying a submatrix times a column in your matrix and adding it to another column. So these were kind of all built with doing Gaussian elimination in mind. And here's another variation. You take a column times a row and update a matrix, and also solving triangular systems. These are all built in. And now we're up to like 66 routines and 18,000 lines of code for the unoptimized version that anybody can download. And they're called the BLAS2, not surprisingly, because now we have n squared data, an n by n matrix, and we're doing order n squared operations to do it all. So if I look at, in particular, this guy, I'm doing 2n squared floating point operations, and it's on about n squared data. So the computational intensity has gone from 2/3 to 2, which is a big improvement, and that was good enough for vector computers at the time. But it's obviously not good enough for today when a factor of 2 is not going to hide the cost of the communication. So that brings us to the next step, and what comes after 2, 3. And so this was a library of BLAS3 routines, the most common one being general matrix multiply. So A times B, any rectangular shapes you want, times a scalar, and then you can add that to C. In addition to that, there's special cases like A times A transpose comes up in Koleski, not surprisingly, and solving not just one triangular system, T's triangular, but many triangular systems. And so now this is another 10,000 lines of code, and you spent assignment 1 optimizing one of these. And now they're called the BLAS3 because finally we're doing n cubed operations, but we're still only doing it on n squared data. And so the computational intensity has gone to n cubed divided by n squared, and it's finally big. We can finally do enough work to hide all the communication costs. And so that is where people temporarily declared victory. And this is all available in all of the MKL libraries, the ACML libraries. All the vendors have teams of people optimizing these routines and doing all of that hard work so that you can just call them. And so, and it's part of the standard math libraries. And just for a little eye candy, the entire library fits on one slide. So if you ever want to do a basic linear algebra subroutine, there's one page you have to look at, and here are all the list of all the routines. So it's sort of a finite amount of stuff. And just so you know that this is, it's much quicker to look at this list than to write it yourself. Okay, so that brought us up to the basic linear algebra subroutines. And now the question comes, how do we rewrite all the higher level routines that people want to do? Solving linear systems, least squares, eigenvalue problems, to get the advantage of the speed of matrix multiply. I mean, if you look at Gaussian elimination or eigenvalue problems, there's no matrix multiplies that immediately jump out at you. You have to reorganize the algorithms to do that. And so starting in 1989 and continuing to this day, there is another library called LAPACK. And so, as I said, the obvious way to write Gaussian elimination, and I'll remind you of that in the next lecture, is you take a multiple of one row of the matrix and you add it to the next row to zero out an entry, and you keep doing that. So it's all natural BLAS1 operations, in fact, Saxby's. And so what we have to do is reorganize all of that in order to do matrix multiply. And that's the detail the next time. But to summarize how far people have gotten, in the current edition of LAPACK, there are some algorithms that you can basically reorganize, and you spend asymptotically all your time doing matrix multiply. And that's linear systems and least squares. So those are successful from this point of view. And then there's a bunch of other algorithms that people still haven't figured out how to spend. You spend half your time doing matrix multiply and half your time doing matrix vector multiply. So that bottleneck remains. And that's for eigenvalue problems in the SVD. And it also has error bounds for everything. The philosophy of this library is if some quantity can be computed, there's another subroutine that will give you an error bound because people want that. And there's lots of variants dealing with symmetry and all that sort of thing. So how much code is this? The last time I did the count, there was about 500,000 lines of code because there are just a lot of variants of all this stuff. And then there's another 360,000 lines of test code. Because over time, we collect every user's nasty corner case where something goes wrong and put it in our test suite, and to make sure that this stuff, it only gets better over time. So that is part of the development of these things. And so the last release was in April 2012, so there's sort of ongoing development because there's always something else to do. And in fact, we're gearing up for a large project to sort of redo a lot of it based on the new algorithms that I'm going to be telling you about. So this is all just the sequential case so far, dealing with memory hierarchies. Parallelism, where does that come from? So is that library I just told you about is LAPACK parallel? Well, when you call the BLAS, if you call matrix multiply and that's all parallelized, then you'll get parallelism from that. And if you're in a shared memory environment, you could just imagine doing that. But that's not going to be good enough for the big distributed memory machines like Hopper and so forth that people want to use. And so there's another version of this library called ScalaPack for Scalable LAPACK, which is running in parallel. Same team is putting that together. And that's for distributed memory. It uses MPI. It has rather more complicated data structures so that you have to lay out your matrices across all the processors by hand in a way that I'll show you later. And since it is a more complicated programming environment, it's currently only a subset of all of LAPACK's functionality. And all of that's also available there. And there's plenty of class projects if anybody's interested to implement some of the new algorithms we've discovered. So these are widely used. They've basically been adopted by all the vendors as the basis for their own libraries. So when we collaborate with the teams at Intel and the MathWorks, for example, they start with LAPACK or ScalaPack, and they may optimize it for their particular architecture or add their own interfaces, but it's basically all of this. But there's still a lot of people who go to the regular website, the public domain website, the 7.5 million last year, to download it. And one of my favorite stories is a cover story of Nature from a while ago. And the science problem that they were trying to answer is the universe going to expand forever or not? And so what they did is they launched a camera on a balloon that aimed a radiation detector at the sky and measured the cosmic microwave background radiation in every direction. So for every pixel on the sky, it got a signal back. And for every pair of pixels in the sky, it could compute the correlation between the signals, between this direction and that direction. And it got an n by n matrix, where n is the number of pixels of all those correlations. And depending on the eigenvalue properties of that very, very large dense matrix, they could say which theories of the universe was the data consistent with. And so there were sort of three theories. One was that the universe will continue expanding forever, and in fact, it'll accelerate. And so one night you could walk outside and imagine, look up at the sky, and nothing's there. So that's one option. Another option is that it will eventually stop accelerating and begin to collapse again, and there'll be another Big Bang. So you could walk out in the middle of the night and look up and say, uh-oh, so that's another possibility. And the third possibility is that the universe is, I think, flat is the technical term, which means it'll accelerate forever, but it will slow down. It'll decelerate continuously forever, and it'll sort of reach a steady state. And that turned out to be what's consistent with the data. And that involved this very large, dense eigenvalue problem. So we will have actually a guest lecture later in the semester because they are now putting up satellites with far more detailed information, many more pixels of data than were collected with this balloon, and they can't do dense linear algebra anymore because there's billions of pixels and so forth. But at this time, that was the best they could do. Okay, so this is the last history slide before I go into the technical stuff. So what about current, more interesting architectures? So here, a lot of people are asking, what about multi-core? What about GPUs? What about heterogeneous platforms? So these are two ongoing projects. that are working on this. So and I will have more material in the next lecture about how these codes are organized. So Plasma uses an idea called DAG scheduling. You organize your computation into a directed acyclic graph, a DAG, of computations. Each computation is like a BLAS call on a local processor. And you try to schedule those as densely as possible on all of your multi-core processors. And Magma uses a sort of a similar technique, but it's designed for heterogeneous machines. So some of those subroutine calls may execute on a GPU, some of them may execute on the CPU, and you have an interesting scheduling problem to keep everything busy and not spend too much time communicating between the CPU and the GPU. And let me say that other people are also trying to develop in this area. Flame is a project. And remember the BLAS 3? Well, the community did try another standards effort. But at this point, there's just too much innovation going on for people to want to really standardize too much. So that was an older effort called the BLAST 4. So that's history. And so now I'm going to go back to the basics and talk about the algorithms and lower bounds and how to attain them. But are there any questions before I go on? So let me go back to the basics and remind you why avoiding communication, which means moving data, why that's an important thing to do. And so when we think about designing an algorithm, there are going to be two costs. One is the arithmetic, the floating point stuff. And the other one is moving data. And I mean two things by that. I could mean either moving data in a memory hierarchy, so between the DRAM and the cache, or between L1 cache and L2 cache, and then also between processors over a network. So here I have a 4-processor machine communicating over a network. So let me try to contrast these two costs. So this is a bit of a review. The model that we're going to use to ask ourselves, have we designed an algorithm that is close to hitting the lower bound, is we're going to count three things. We're going to count how many floating point operations it does. We're going to count how many words it moves, between one processor and the other, or between levels in the memory hierarchy. And we're going to count the number of messages. So the messages are the number of blocks into which the words have been decomposed. Because it's usually much faster to take a continuous chunk of data on one processor and send it as one big chunk to the next one instead of lots of little messages. And in fact, the latency that this gets multiplied by is much, much larger. So then there are these three hardware parameters: the time per flop, the time per word move, that's the reciprocal bandwidth, and then the latency, the extra cost per message. And all of these three hardware parameters are orders of magnitude apart. And so the time per flop, I could be doing 1 billion floating point operations per second. The bandwidth, the time to move a word could be 10 or 100 or 1,000 times slower, and the same thing for the latency. And these gaps are growing exponentially with time. And so here's some somewhat old data, which says how much these costs are growing apart. And so the time per flop, that's governed by Moore's law. It's getting faster by 59% a year. And the bandwidth and the latency are also getting better, sort of, but they're not getting better nearly as fast. And I think I showed you a picture of latency costs on supercomputers in an earlier lecture. And the world's record was set back in 1997. It hasn't gotten better. So to say it's getting better at 5% a year is sort of drawing a straight line through a cloud of data, which isn't really getting better. So everything's getting better, but you can see that over time, this guy is going to become the bottleneck, or that guy is going to become the bottleneck, and not the arithmetic. And so obviously we want to minimize communication to save time, but that's not the only reason. So here's some other data on hardware to explain why we want to do this. This is the amount of energy it costs to do all the basic operations in a machine. So the vertical axis is picojoules on a log scale. This is floating point arithmetic. This is moving data on chip. And this is moving data off chip. Right? So moving data on chip doesn't take a whole lot of energy. But once you move it off chip, it's like 1.5 orders of magnitude more to move something, because you have to charge up a pin, the electrons have to move a great distance. It just takes a lot more work than it does to do the arithmetic. And there's both blue and red lines here. The blue is today's technology, 45 nanometer. And the red is a prediction of what it's going to look like in a number of years, an 11 nanometer technology. And everything is going to get better. That's still true. In fact, arithmetic is going to get 10 times cheaper. But the other guys are not going to get that much cheaper. So now we're talking about 2.5 orders of magnitude more per operation cost to do stuff. So, and this is why I color it green, we want to minimize communication to save energy. So that's also a good thing to do. So whether it's your, the battery in your handheld device, or the $1 million per megawatt per year that it costs to turn on your supercomputer, you want to save energy. So our goal then is to reorganize, for the next 2 lectures, linear algebra to avoid communication. Eventually we have to do all the motifs, but this week it's dense linear algebra. I want to minimize it between all levels of the memory hierarchy, you know, moving data between L1 and L2 and between L2 and DRAM, all those different things. Now, sometimes people in this business talk about hiding communication, and that's different, and it's a good idea. That simply means overlapping communication and computation. It means while you're doing arithmetic, you're also pushing data somewhere else. But obviously, you can't get a speed up of more than 2x by doing both of those at the same time, and that's a good thing, but that's not the orders of magnitude we're talking about by not communicating at all in the first place. So we have a lot of progress, but there's still lots and lots of open problems, not just in linear algebra, but in all the other motifs that I'll be telling you about. So let me just review sequential linear algebra, and then I'll do sequential matrix multiply, and then I'll do the parallel case. So here's the naive code that we all started with, that we know is a bad idea. 3 nested loops over I, J, and K, which in the inner loop takes the dot product of the ith row of A and the jth column of B. And if I annotate it by counting how much data I move, then you can see that I have to read I have to read the jth column of B into memory inside this loop. I have to read each column. I have to read B n times, and so I'm doing n cubed reads altogether. And so I'm doing as many reads and writes as I'm doing arithmetic, and so this is a bad idea. And so the algorithm that we told you about, again, this is just review, was to block it. And so what I'm going to do is break up my 3 n by n matrices into b by b blocks. I have to choose that block size. And I'm going to call, so A sub ij is not an entry of the matrix, it's a b by b block. And so the easiest way to write the code is still as 3 nested loops, but now the inner loop is actually doing a matrix multiply. That's a b by b times a b by b matrix multiply. And so if I count it all correctly, this is going to cost me b squared reads for each of these 3 matrices, b squared writes for that one, so b squared reads and writes all together. And I'm doing that n over b cubed times, and all together, the number of reads and writes goes down by a factor of b. So the bigger the b, the better. And so how big can I make it? And the answer is that all 3 of these submatrices better fit in cache. So 3b squared is the cache size, and that hits this value of n cubed over m to the 1/2. That's the best we can do with this algorithm. And in fact, it hits the lower bound no matter how you do it. So then I pointed out, and this again is review, is that this is just fine if I have 2 levels of memory hierarchy, some slow memory and then fast memory, which I'm giving a name of size m. But real machines not just have 2 layers of memory, they have DRAM, they have L3, they have L2, they have L1. And so if I had that problem, then I would have to have another 3 nested loops for this and another 3, I'd have 3 more nested loops for every level of memory hierarchy. So if I had 3 levels of memory hierarchy, I'd have 3 times 3, or 9 nested loops. And so the alternative that people determined to figure that out, instead of having another 3 loops for every level of memory hierarchy, is people introduced this idea called a Cache-Oblivious algorithm. And so now this, without the code, in principle, knowing anything about the hardware, without having to know the block size, it just breaks your matrix up into matrices of half the size, n over 2 by n over 2, and calls itself recursively. So this recursive matrix multiply multiplies that n over 2 by n over 2 matrix times that one. And when you do write down the recursion, it also minimizes communication. So this is just by way of review. So what I want to do now is tell you what are the lower bounds that this hits, not just for matrix multiply, but these are lower bounds for this entire dwarf, for all of dense linear algebra. So let's assume that we're going to run an n cubed algorithm. So that means we're leaving out the Strassen kind of stuff that does n to the log base 2 of 7. And in the sequential case, when I only have 1 level of fast memory, so I have huge memory and then fast memory of size m, then the lower bound on the number of words moved is n cubed over the square root of m. That was proven back in 1981. And that was attained by using those 2 algorithms. Now what's known in the parallel case? So this was proven rather later in 2004. So let's suppose that I now have p processors. I want to arrange matrix multiply across p processors, and I want to have a lower bound on how much data moves between processors on that parallel machine. So it's going to depend on the memory. So let me assume that I've spread out my matrices evenly across the whole machine, because if I put all the data on one processor and it did all the work sequentially, it wouldn't have to communicate at all, right? That would be sort of a trivial case. So I want to make sure that everybody's doing one piece of the work. And then the question is, how much does the data has to move between one processor and the other? And the answer turns out to be almost the same. It's the number of flops done per processor, that's n cubed over p, and it's still divided by the square root of the amount of memory that each processor has locally. But the question is, what's that, right? Because my matrix is now spread out over the whole machine. I may only use a little bit of the memory of each processor, right? I don't need the entire memory on each processor in order to do a matrix multiply. So the question is, how do I choose M? It's not a cache size anymore. And so the answer is, if I have an n by n matrix, or 3 n by n matrices, and each processor gets one piece of the data, that's how much memory I'm effectively using in each processor. So the memory per processor to apply this lower bound is 3n squared, the total storage, divided by p. That's what each processor has. And that's what goes in the M. And when I plug that in, this turns out to be the lower bound. So again, the assumption is it's all load balanced. Each processor is doing its own fraction of the work. And the memory is load balanced. Every processor has one piece of the data. Then the lower bound is n squared over the square root of p. That is how much communication is necessary.
If you do some of those communication avoiding strategies where you recompute things locally and that uses more memory, does that get factored into
I will get into that later in the talk. And there's an assumption here, which is we only have one copy of the data spread out over the machine. And as was just pointed out, this lower bound, once we generalize it suitably, it doesn't really assume, you don't need to assume you only have one copy of the data. I mean, that's a perfectly natural assumption. But maybe you have more local memory. Maybe you could afford to have 2 copies or 3 copies or 4 copies. And then the lower bound decreases, right, proportional to how much memory you potentially could use. Is there an algorithm that attains it? And a couple of years ago, we figured out that there was one that actually can go faster and faster if you use more and more memory and to replicate the data. And so we will talk about that by the end of the lecture. But I'm going to start by telling you about this classical version, which made the most reasonable assumption that it only had one copy of the data spread out over the machine. And it's attained by something called SUMMA, Scalable Universal Matrix Multiply Algorithm. A very pretentious name, but that's what people call it. And then Cannon's algorithm. OK. So, fine. OK, so now what I want to say is how this generalizes. All of that was known since 2004, just for matrix multiply. And what turns out is it's true for basically everything that sort of smells like 3 nested loops. So here's what's true. Let M be the fast memory size, which could be the cache size in the sequential case, or n squared over p, for example, in the parallel case. And I'm also just going to count the number of flops done per processor. And if I'm doing dense linear algebra, that's going to be n cubed or n cubed over p. But it doesn't have to be. I could be doing sparse linear algebra. Then it turns out that the number of words moved is the number of flops, whatever that is, divided by the square root of the fast memory size. And this is true not just for matrix multiply. It holds for all of the BLAs, for Gaussian elimination, that's called LU decomposition, for the QR decomposition, for eigen SVD, which is MATLAB speak for eigenvalue problems, and the singular value decomposition. It's true for tensor contractions. It's actually true for some whole programs where you have a sequence of these calls, and you're doing multiple linear algebra operations. For example, if you're computing a power of a matrix, a to the 10th, sometimes you have to do that, then that entire computation, the lower bound applies to that. It applies to both dense and sparse matrices. And in the dense case, that's n cubed, but in the sparse case, it's going to be much, much smaller depending on where the zeros are, non-zeros are in your matrix. But it's still the same lower bound. It applies to both sequential and parallel algorithms. So in the sequential case, the number of flops is whatever your sequential algorithm does. But in the parallel case, this theorem is true processor by processor. So no matter how many flops one processor is assigned, this is the lower bound on how much that processor has to communicate. So you can sort of get a global bound by taking the max of what each processor does. And as I said, it basically applies to anything that smells like 3 nested loops. And that's sufficiently general, and there's a rather theoretical model of what that means. It's sufficiently general to include some graph theory, because there are some graph theoretic algorithms like Floyd-Warshall for all pairs shortest path that also look like matrix multiply, similarly enough, in order for all these lower bounds to apply. So given these lower bounds, our goal naturally is to, number one, ask, do standard algorithms attain them? You know, the Gaussian elimination that we all learned a long time ago, and the answer is no, they do asymptotically more. And then to determine new algorithms that do attain the lower bounds. And that's an ongoing process, but let me say that it has been done for many standard linear algebra algorithms, at least on paper, if not in implementation. And hopefully, some point, probably not today, I will sketch the proof of this theorem, because it uses some very classical geometry in pure mathematics, and it's very pretty, if you like that sort of thing. Okay, so let me now plug in some values here to see what this theorem actually tells us. And I'll just do it for dense linear algebra. So in the case of dense linear algebra, the number of flops is n cubed. And so I get n cubed divided by the square root of the cache size in the sequential case. And the number of messages, now where does this lower bound come from? If this is the number of words that I have to move, then the question is, what's the largest message size, right? So a lower bound on the number of messages is the number of words divided by the largest message size. And the largest message size is obviously the whole memory, right? That's kind of a trivial upper bound on the size of the largest message. So this is a factor of m smaller than that. So that's why it goes from 1/2 to 3/2. So that's very simple. So if you're counting messages by cache lines, then this would only be a factor of cache line size, smaller. So this is kind of a very global lower bound. So what about the parallel case? So let's suppose that I have n by n matrices, and I'm spreading it out in a load-balanced fashion over p processors, and each processor is going to do so n cubed over p floating point operations. And I'm also going to assume, temporarily, I'll fix it later, that I only have one copy of the data, and it's all load balanced. So that means each processor has a local memory size of about n squared over p. So if I plug this into the number of flops and this into the local memory size, the number of words moved is n squared over the square root of the number of processors. And the number of messages is the square root of the number of processors. So that is going to be the lower bound that we're going to try to design algorithms to attain. So, and I'm happy to say this won a Best Paper Prize last year for this generalization. Okay, so the next question, and I've partially answered this already, is that do the standard libraries that we've built over many years attain these? And the answer is mostly not. They were not designed with this goal in mind, and they're often fast, but there's a lot of situations in which they could go asymptotically faster. And we've been busy designing new algorithms that do attain these lower bounds. And so the goal for the algorithm design, whether you're, if you're a user, this means you want to find a library where somebody's done the work already. If you're a library builder, these are your goals. You want to minimize the words moved, and that means between every level of the memory hierarchy. You want to minimize the number of messages sent, and sometimes that means we need different data structures. I mean, we're used to storing our dense matrices column by column or row by row. If you do that, you can't hit this lower bound. We need to have different data structures in order to hit the message lower bound. So that changes the interfaces that everybody's used to. As I mentioned, we want to do this for multiple levels of memory hierarchy. And the cache-oblivious algorithms that I told you about earlier, those would often be the simplest, but in practice, you can't ignore all the details. And in particular, for some of those cases, for some of those algorithms, the cache-oblivious algorithms don't always minimize the number of floating point operations. So if you're running a problem that's so small that it fits in L1 and you'd still like to run as fast as possible, in that case, there is no communication. You just want to minimize flops. And sometimes the cache-oblivious algorithms don't minimize the number of floating point operations. So you need some sort of hybrid between different algorithms. And so, as I said, this is attainable, at least in theory, for nearly all of dense linear algebra. We have some prototype implementations. And if you're interested, there's lots of class projects. Now, in the sparse case, there's really only a few examples where we figured out how to attain the lower bound, because it depends very much on the sparsity structure of your matrix. If you just throw in random non-zeros, then it may not be attainable. I mean, it's still true, the lower bound, but nobody has any idea of how to attain it. There are some cases, though, where there are common sparsity structures, and you have to make some assumptions about the common sparsity structure, and we'll do that in a future lecture, and then it is attainable. Okay. So that's the end of the first part of the talk, which is history and motivation in the lower bounds. And so now I'm going to go up a level and talk about what's in this dense linear algebra motif, how it's all structured. And I mentioned there's lots of routines and lots of kinds of matrices. And then I'll go back to parallel matrix multiply and talk about how to attain the lower bound. So what could, if you were to sit down and either build a library or ask, try to read a table of contents of a library, you could ask what goes into one of these things. Well, so here is kind of a cartoon of all the stuff that could go in. You could say, for all linear algebra problems, so solving linear systems, least squares, eigenvalue problems. Then you could say, for all matrix problems and structures. So that means, for example, real, symmetric, non-symmetric, banded, triangular, all those different flavors. For all the data types, you could be real, single precision, or complex, very wide precision. We've even had a request for finite fields, so people could do cryptography, right? There's all sorts of imaginable data types. And then, of course, there's all the different architectures and networks that people want to run this stuff on and have it be run as fast as possible. Sequential, multi-core, distributed memory. And then, of course, everybody has their own favorite programming language, and they want to call it, whether it's from C or Fortran or Python or R or any of those things. We want to produce the best algorithm, in principle. and the word best is not well defined, because for some people that means go as fast as possible. And even if the answer is slightly not quite as good as it could be. And other people want the most accurate answer, right? And they might even want an error bound. They want a guarantee. So there is no one best algorithm. And so this is sort of a cartoon of several, quite a few people's lifetimes work if you want to do that. So we clearly need to prioritize. And in fact, many people try to automate this and automate the generation of these various parts. And then there's many levels of interfaces. So there's the simple driver, the equivalent of A/B. And then there's the stuff for experts where you can have some error bounds and use some extra precision and maybe only want a subset of the answer. And then there's even lower level routines that people want to call, the BLAs and other things. So let me just give you a little tour through what the table of contents, again, looks like. And so here, for better or for worse, are all the different structures of matrices that are available that you need to sort through that are supported. And most people obviously just want a general matrix. It's a square n by n matrix with no particular structure. But some people have symmetric matrices. So they're all the different flavors of symmetric matrices. And they could be Hermitian, which is the complex case. They could be real or complex and just perfectly symmetric. And of course, they have other structures going along with that. They could be banded. They could be tridiagonal. And what's packed? So if your matrix is symmetric, you only need to store half the data, right? Now, on the other hand, if you're storing your matrix column by column, how do you store only half the data, right? There's sort of this empty upper half of the triangle. And so there's this other data structure where you pack the whole thing, all your n squared over 2 numbers, into this rather more complicated data structure, and it doesn't run nearly as fast. But you only use half the storage, right? So there's a storage performance trade-off. Sometimes, and there's yet one more flavor of symmetry, where you have an extra property called positive definiteness, which means all the eigenvalues are positive, because there are a lot of, if you know that, you definitely want to take advantage of it. You can go faster. And then there's, of course, triangular matrices, which could include trapezoidal and packed and pairs of them and all those sorts of things. So this is the complexity you have to work through. So we have tried to organize this to make it easy to find what you want. And so this is old-fashioned technology, but books are available, and they're freely available online. So where we try to supply decision trees where you can sort of work your way through and find the best code. And even the government is involved. So let me try to show you this web page. This is gams.nist.gov. GAMS is the Guide to Available Math Software. And this is provided by the NIST, the National Institute of Science and Technology. And it basically gives you a problem taxonomy for all of applied mathematics. And it tries to give you sort of this tree where you can say, well, I need to do integral transforms, or I need to do optimization, I need to do linear algebra, and it gives you pointers to all of the code that they try to keep track of, right? They don't necessarily keep totally up to date, but let's just try it and see what happens. So I'll click on linear algebra. Maybe. There we go. And it says, and these are keywords, and so here's all the things you might be interested in doing. You might want to solve linear equations or compute determinants. Some people want to do that. Eigenvalues, eigenvectors, singular value decomposition. So let's click on solving linear systems. And so now you get yet more choices: real, non-symmetric, real, symmetric, complex, Hermitian. Tries to give you some choices. Let's take the most general case, real and non-symmetric. And now it's asking you, what is your data structure? Is it general or band or sparse? So there's sparse stuff too. That's not today's lecture. Let me go general. And then finally, I think it has pointers to lots of subroutines. This is the so it has LAPACK and many other libraries that you can now just click on and get to. So if you are just a user who wants to find the best thing, you clearly at this point don't know which of these is the fastest. You don't know which one is going to run in which architecture. They haven't gotten there yet. But these are attempts to make these things easily to find what you want. Okay. Oops. All right, so this is a PowerPoint glitch. So we are, why is it doing that? Let's see if I have to restart. Microsoft error reporting. Uh-oh, okay, give me a moment. I have to restart PowerPoint. Let's hope for the best here. Okay, maybe we'll come alive again. Okay, so we are now done with the structure of the dense linear algebra dwarf. I've sort of given you the table of contents. And now we're going to go back to parallel matrix multiply and ask ourselves how to do it as fast as possible and attain the lower bound. So the first question we have to ask ourselves is, if it lets me, thank you, is what is a data structure? And here are a sequence of perfectly natural data structures that I want to walk you through until I get to the final one, which is the one we're going to use. And so the most obvious thing you might say is if I have 4 processors numbered from 0 to 3, each one gets a quarter of the columns. That's going to turn out to be asymptotically impossible to hit the lower bound with this particular data structure. But I'll have a couple of slides to implement it anyway. But there's another reason to see why this is going to be a bad, if perfectly natural, layout. So imagine I'm doing Gaussian elimination. And if you remember how that works, I'm going to update. I'm going to take the first row of the matrix, subtract it from later rows, zero something out. And at every step, I'm going to have finished processing a bunch of leading columns, and I'm going to have done a bunch of leading rows. So let's suppose I get down this far. I've made that much progress in Gaussian elimination. Processor 0 is going to be completely idle at that point. It's going to have no more work to do. Only processors 1, 2, and 3 are going to have work to do. So this has terrible load balance. So that is some hint. So here's another example where I avoid that load balance problem. Again, every processor gets 1/4 of the columns, but now each processor gets every 4th column. So whichever subset of this matrix of the columns I take, it's perfectly load balanced. But now, if you can see the problem, is that I don't have any dense matrices to do local matrix multiplies on anymore, right? So if processor 0 owns only the blue columns, they're all spread apart, and there's no matrix multiplies. There's no local dense linear algebra that I can use to get good local performance. So let me try to compromise between those two layouts. And I'm going to pick a block size B, so that when I do a local B by B multiply, hopefully that'll run fast in the local processor. And then every processor will get every 4th block column. And so the problem with this one now, again, think about Gaussian elimination. One processor owns all of this stuff. So that means that there's no parallelism whatsoever in processing the first B columns. That's a sequential bottleneck. So that's not going to work. And so in fact, I have no choice but to have a 2-dimensional layout where processors share both rows and columns. And so here's the simplest way I could have a 2-dimensional layout, where each processor owns a quarter, a square block. But again, I have that load balance problem that once I've made progress in Gaussian elimination, and I'm only working on the southeast corner, the other 3 processors are idle. So that's a bad idea. So here's the winner. Here is going to be the data structure that we use basically for everything. And it's called a 2D block cyclic layout. And so if you can see there, I've color-coded it to show you what processor 0 owns. So I break up the processor grid into a square root of p by square root of p grid, in this case 2 by 2, and each processor gets a little b by b block. So each of these is a b by b block, and so now I have parallelism across the rows, across the columns. If I take a submatrix, everybody owns a quarter of it, so I get load balance. And I have little dense b by b matrices, which give me high performance locally on each processor. So this is the natural data structure from the point of view of getting high performance. It's not natural for most users. So this is one of the issues with using these kinds of libraries. But let me go back to this layout and do as best I can and see why I can't actually hit the lower bound. So let me just warm up with the notation. So I'm going to talk about matrix vector products first, just to see what that looks like. So I want to do y equals y plus a times x. Everything, a is a square matrix. And again, suppose I have 4 processors numbered from 0 to 3. And so the easiest way to do it, let me use this layout where every processor owns 1/4 of the rows. So processor 0 owns that submatrix, processor 1 owns that submatrix. And I'm going to split up the vectors x and y the same way. So each processor owns 1/4 of the entries of x. So here's the vector x, and there's the vector y. So processor 0 owns that bit of y, processor 1 owns that bit of y, and so forth. So the obvious algorithm is for each processor, I need to broadcast the piece of x that I own to everybody. Then when everybody owns x, I can take my big submatrix, my a sub 0, multiply it by the entire x vector, and update just the local value of y. And so that's a perfectly natural way to do it. That's going to be the algorithm we're going to mimic in the matrix multiply case. I could also do it with a column layout. And in that case, I wouldn't. So here I have this communication. Where's all the communication? I have to broadcast y. Excuse me, I have to broadcast x. That's the only communication I have to do because I already own all of the matrix that I need. And my piece of y that I have to update is local. So that's all the communication. Now, if I were to change the layout and store my matrix by block columns instead of by block rows, I wouldn't have to broadcast x anymore because I'd be multiplying a tall, skinny block of A by my local stored piece of x. But instead of communication to broadcast x, I'd have communication to update y, right? Because every processor would own a component of y, and they'd all have to be summed, so that's a reduction. And so here's the compromise. It's a 2-dimensional layout. Here I have 16 processors numbered from 0 to 15. And here is my vector x, there's my vector y. And so now I'm going to do both communications. I need to broadcast this piece of x. To whom do I have to broadcast it? Processors 0, 4, 8, and 12. So only square root of p processors need to participate in that. And then I still need to do a reduction to accumulate this piece of y, but only 4 processors, only a square root of p processors need to participate in that reduction, processors 0, 1, 2, and 3. And so that may reduce the communication because all the row communication can happen in parallel and all the column communication can happen in parallel. So that's what the layout would look like for matrix vector multiply. So, but now I'm going to go back and do matrix multiply and do a little bit more of the details. But that's sort of what the data structures look like. So let me do matrix multiply now. So I'm going to just keep everything square using the usual n-cubed algorithm. So I'm going to do 2 n-cubed flops. And so what do I have to do? I have to choose a data layout, which could be 1D or 2D. Once I've chosen the data layout, I need to make some assumptions about the topology, which processors are going to communicate which others. And so I'll do sort of some simple ones first, which are easy to think about, but we'll see that they're pretty far from the lower bound, where everybody's connected in a ring, basically, or a torus. And so, and then I have to do my accounting so I can compute the complexity. So what am I going to do? I'm going to count the number of messages. And for each message, I'm going to count, there's a latency cost, the cost for packing the message, pushing it into the network. And I'm also going to count how many words are in the message, that's n, and I'll multiply that by the time per word, or the reciprocal bandwidth. And so I'm going to count flops, I'm going to count the number of messages, multiply that by alpha, and the number of words, multiply that by beta. So we remember the notation. And I'm going to say, how well do I do by asking, what is this sequential time to run the algorithm, which is just 2n cubed, divided by p times the parallel time. Now, if my algorithm were perfect, the parallel time would be 1/10 of the serial time, and this efficiency would equal 1. The question is, how far away from 1 am I? OK, so let's try it in the naive way first and see how close to the lower bound I can get. So I'm going to assume my matrices are laid out on just by block columns. So each processor gets 1/10 of the columns. And so my notation is going to be that A sub I is going to refer to that whole submatrix. So it's going to be an n by n over p submatrix that's owned by processor I. And Bi and Ci are going to be the same thing. And this particular submatrix, B sub ij, is going to be a little locally stored n over p by n over p subblock. So it might be something that fits like that. And so what I need now to do is say, how do I formulate matrix multiply to look like this? Well, to compute the ith column of C, I'm going to update it by taking the jth block column of A and multiplying it by each one of these blocks. So this block of A will get multiplied by that block of B. That block of A will get multiplied by the next lower block of B, and so forth. So that captures the algebra in that little formula, which I'm just going to repeat here at the top of the slide. So now I have to do my accounting. I have to count the number of messages sent and the number of words moved. And I'm first going to do a really naive machine, which may be the kind that's in your office, all of the different processors connected on Ethernet. And it's not a very good parallel machine. I'm just going to talk about it because it sort of appears naturally in everybody's office, at least the old kind of wired offices. And then I'll consider a more interesting parallel machine where everybody is connected on a ring. So you can talk to your nearest neighbors to your left and right. So it's going to be the same algorithm, but because of this different topology, I'm going to get very different complexities. So let me do the first one. And so here's the naive algorithm. So this is going to assume that each processor owns this block column of A, B, and C. And it's on a bus. It's on an Ethernet. And that means that only two processors can talk to one another at the same time. Because when they're sending bits along that wire, nobody else can talk to one another. That's the way Ethernet works, a little old-fashioned. So here's the algorithm. Each processor has its own processor ID, so I'm going to call myself myproc. So this code runs on every processor, and it's identical. The only thing that changes is my processor number, which runs from 1 to p. So everybody has all the data that they need to do this in parallel. They're going to take their locally stored block column of A, multiplied by that little square block of B, and update their locally stored block of C. But now, in order to keep going, I need all the other blocks of A. So myproc, it doesn't have to communicate C. It has all that stored. It doesn't need to communicate B, but it needs all the rest of A. And so what I'm going to do is for every pair of processors, I'm going to let I and J independently run from 0 to p minus 1. And I'm going to send whatever data processor I has to processor J if it needs it. So this is sort of pseudo MPI code. So if I'm looking at the pair I comma J, then processor I sends its chunk of A to processor J, and when processor J gets it, it does this bit of code. And so if I do this cost, this is a terrible algorithm, because there's no parallelism whatsoever except in that very first line when everybody has all their data locally. So what is the cost of the inner loop? The computation is going to be a matrix multiply. This is an n by n over p matrix times a n over p by n over p matrix. And there's the cost of the inner loop. And the communication is sending a whole block of A. So it's an n by n over p submatrix of A, so it's n squared over p altogether. So that's the cost of this inner loop. So now I just have to multiply by how many times do I execute the inner loop. So let me just repeat. There's the inner loop costs, and both computation and communication. And since there's really no parallelism, all I have to do is multiply it by p squared, because that's how many times I execute the inner loop. And so the total cost is 2n cubed. There's no speed up in the arithmetic at all. I'm doing 2n cubed floating point operations. The number of messages is p squared, because every processor has to talk to every other processor. So that's basically p squared messages. And then the entire matrix eventually has to visit everybody else, so it's pn squared. And so this is even worse than the serial time. So Ethernets are bad ideas. So now let's go on to the same algorithm, but now on a more sensible situation where all the processors are connected on a ring, and everybody can talk to their nearest neighbor simultaneously. So one can talk to 2, 2 can talk to 3, 3 can talk to 4. All of that happens in parallel. So here's the code. what I'm going to do is take my tall, skinny piece of A, my n by n over p submatrix of A, and copy it into a temporary. So I need some extra memory. And then I will do the same thing I did before, which is all the stuff I can do locally. I don't need any information. This line of code is the same as before. And now everybody takes their block of A and sends it to their neighbor, to their nearest neighbor. So the whole matrix A just kind of gets rotated around the ring by one block. At that point, and all that communication happens in parallel. So I get my block of A from my processor. I send my data to my processor to my right, so from my proc to my proc plus 1. And since it's a ring, it's mod p, so it goes around in the circle. And then I get the information from my neighbor to the left, that's my proc minus 1. And now I have all the information that I need to multiply that new block of A times my appropriate little local stored block of B. So all of that happens at the same time. And this is actually the same idea in sharks and fish, the same idea as in gravity, right? So there's a bunch of particles in each machine, and I compute all the interactions between those particles. And then at every step in the algorithm, I take my particles and I send them to my neighbor. And I compute all those interactions. And they move over to the next neighbor. And all of that happens in parallel. It's the same pattern for doing sharks and fish, for doing particle simulation, as it is for doing matrix multiply. So these are the sort of patterns we should recognize. And just as that particle simulation doesn't hit the lower bound, this doesn't hit the lower bound. But there is a common pattern that does hit the lower bound for both matrix multiply and n-body. So this is one of those generalizations that we will see. So let me take this algorithm and do the complexity and see how good we are. So the inner loop, what is it doing? It's receiving one message from my left and sending one message to my right. So I have two messages. Each one of them costs one latency cost of alpha. And I'm sending one matrix whose total size is the same as before, n squared over p. And then I'm doing my local matrix multiply. That's the inner loop. And I'm running the inner loop p times. So I just take the cost of the inner loop and multiply it by p. And here's the total cost. The flops scale perfectly. N cubed, 2n cubed, the serial flop cost goes down to 2n cubed over p. So that's perfect speed up. That's what I wanted. And now the complexity, the communication, I'm sending p messages. I have to talk to my neighbor p times. And the matrix is moving around exactly once. So the total amount of communication is n squared. And if you insist on having a one-dimensional layout, this bad one-dimensional layout, then this is as good as you're going to get if that's your starting layout. And it's easy to see why, because this submatrix that's been moving around, it has to visit everybody at least once, because that's what the dependencies in the algorithm are. So let's ask ourselves how efficient this is. So this is nowhere near the lower bound, right? So remember, the lower bound was that p should be a square root of p. And this should not be n squared. It should be n squared divided by the square root of p. So, I mean, this is not anywhere near the lower bound, but it's certainly better than the one we had before. But let's ask ourselves, how efficient is it? So if I run a really, really big matrix on not too many processors, how close to perfect efficiency do I get? So what do? I take the sequential time, that's 2n cubed, and divide by p times this parallel time that I just computed, and ask how close is that to 1. And so here is the formula, and if I ignore all the constants, it's 1 over 1 plus order of p over n. So what does that tell me? That tells me if my matrix is really big, n is really big compared to the number of processors, so that p over n is small, then my efficiency will be close to 1, and I will have good speed up. Even though I'm communicating much more than necessary, once the problem gets big enough, it's basically all dominated by the arithmetic. And so the communication isn't so important. That's what this tells me. But I really want to communicate less than this because I want to have as good efficiency as possible, and I don't always have huge matrices. I want to be efficient on smaller matrices as well. So, just to remind you, we're going to have to go back and use this two-dimensional data structure in order to hit the lower bound. So that's where we are. So here is the summary of the best algorithms historically that assumed that you had one copy of the data. The first one is called summa, scalable universal matrix multiply. And that does attain the lower bounds, except for some factors of log p. But otherwise, it's pretty close to lower bounds. Now, that was not historically the first one. The first algorithm was by someone named Cannon in his PhD thesis. But he had a bunch of special assumptions in there. It's a beautiful algorithm, but I'll tell you the more general one. He had to assume that A and B were square and that the number of processors was a perfect square. But anyway, he gets credit for having hit the lower bound first. So then, after I tell you about summa, I'll tell you about the 2.5 dimensional version, and you'll see why that little adjective shows up. This uses more memory to communicate even less. So when you can afford to have 2 copies of the data or 3 copies, it can take full advantage of it and communicate as little as possible. And then I'll say a little bit about Strassen's algorithm, because Strassen, you can also ask the question, how much does it have to communicate? And there are other lower bounds that apply to Strassen, and there are algorithms that attain that as well. I'll just say a little bit about that. So here's summa. So this idea has appeared many times. I'm going to use the description from this particular paper. And this is actually the algorithm that's used in practice. If you look inside of Scalapack, which is the library for dense linear algebra and distributed memory machines, it uses this particular algorithm. Okay. So here's just to tell you what the algebraic formulation is going to be. I mean, there are many ways to write down the nested loops for matrix multiply. So here is the usual description of matrix multiply as nested loops. And so what I'm going to do is write it as an outer product. So here's how you can think of matrix multiply as take the first column of A times the first row of B. So that's a column times a row. That gives you a rank 1 matrix. You do that for k equals 1, the first column in row. Then you do it for the second column in row, add another rank 1 matrix. And you do that for all k pairs of columns and rows from 1 to n. So that is an outer product formulation of matrix multiply. But I could also think of it blockwise. I could, for example, take the first 4 columns of A and multiply them by the first 4 rows of B, add them. Then take the next 4 columns of A, multiply them by the next 4 rows of B, add them. And so do it in a blockwise fashion. And that is what summa is going to do, that particular organization. So let me draw a picture of what the algorithm does. And so here I have 16 processors laid out in a 4x4 grid. And so here's the matrix A, there's the matrix B, and there's the matrix C. And I'm trying to color code it so that A is red, B is blue, and C is green, so we can sort of see how it works. So each of these submatrices now is going to be, so my whole matrix is n by n. This processor grid, there are p processors altogether, so there's square root of p by square root of p processors. And so that block right there is n divided by the square root of p by n divided by the square root of p. That's the size of each of these little square blocks. So what I'm going to do in every step in the inner loop is I'm going to take this block column of A in red times this block row of B in red, multiply them, and add them to all of C. So that's going to be the block formulation. But what does one processor do? What's one processor's responsibility? So suppose I want to update that little green block of C, C sub ij. What I'm going to do is take that subblock of A in red, that subblock of B in blue, there they are, multiply that times that and add them to C. That's going to be the inner loop of the algorithm that does that particular one. And I'm going to do that for all of these blocks K. So if this is B columns, there are going to be n over B of these block columns, red block columns. And so I'm going to have a loop over K going from 1 to n over B and do all of these red times blue multiplications. Okay, so that's all there is to the algorithm. Oops, I forgot to say, where is the communication involved? So in order for C to do this work, in order for C to multiply that red block of A times that blue block of B, it has to get them. So that means that this processor who owns the red block of A has to broadcast it to everybody in its row. So that's what these arrows mean. Processor A has to take its block and broadcast it to everybody in its processor row. This block of B has to be broadcast down to everybody in its processor column. And so now, when the green processor is ready, it receives the red, receives the blue, and it can do the multiply. And everybody in that block row and block column will have the data that they need. So that's where all the communication is. And so having said that in pictures and with arrows, I can now write a few lines of code that actually do that. So there's the same picture as before. And so what I'm going to do is for every one of these block columns, how many of them are there? There's n over B, because there's B columns in there. What I need to do is for every one of these block rows, I need to take this. So for all means this happens in parallel for every one of these square root of p block rows. Whoever owns that block broadcasts it to the whole processor row. So this loop says everybody broadcast that simultaneously, and that one simultaneously. And we're just going to use the simplest way to think of it. It's a broadcast. Think of a binary tree. We've talked about broadcast before. Then what we're going to do is this block is also going to get broadcast down. And this block is going to get broadcast down again, just a binary tree broadcast. Then this processor needs to have some space, so it's going to receive the red block into something, I'll call it A call. It's going to receive the blue block into something called B row, and then it does a local matrix multiply. So this is all the local work, and hopefully that'll run at the speed of your highly tuned local matrix multiply. So that's the algorithm, and so now I can actually annotate it and say how much does it cost, and add it all up. So here's the code again, and I've only put in a few comments to say where all the costs go. So let me just, in the inner loop, say how much communication there is and how many flops do I do. So this is a broadcast. How big is this matrix? It's n over root p by b. So its total size is b times n over root p. And since I'm doing a tree, and a broadcast tree, how many leaves are in the tree? Square root of p. So it's log square root of p. And the number of messages will be the depth of the tree, which is log square root of p. This is the same thing, so that's the cost of the inner loop. And then the matrix multiply is, well, this matrix n over root p by b by n over root p, multiply all that, there's the flop cost. And so let me add it all up. I'll take the cost of the inner loops, multiply by the number of times I execute them. And the total number of words moved is my lower bound, n squared over root p, times log p. So it's just a hair bigger than the lower bound. And in fact, if I were to not just use a simple binary tree, if I were to pipeline it, you could get rid of that log p factor. So without going into the complexity of that pipelined broadcast, we basically hit the lower bound. What's the total number of messages? It's log p times n over b. Now what was my goal? My goal was the square root of p, right? That doesn't look so good, right? Because there's a factor of n there, and n can be a lot bigger. But if I choose b close to the maximum, and the maximum is, each processor sends everything it owns. So the maximum would be this red block is actually the whole thing. And I may or may not want to do it that way. But if I choose b that close to that big, this lower bound approaches the square root of p. So I do have that possibility to get close to that lower bound. And the number of flops actually, is just fine. The number of flops speeds up perfectly, 2n cubed divided by p. So let's look at some performance data and see whether this corresponds to this model. And so this is some old processors, but it doesn't matter so much. It tells us the story that we expect. And so what I'm going to show you is some performance data on a bunch of different machines for a bunch of different processor sizes, not very large, mind you, but like 4, 16, 64 processors. And there's a particular block size. B was chosen here by tuning it. And for a whole bunch of different matrix sizes. So this data tells you the raw speed. I think it's more interesting to look over here, which is the raw speed divided by the upper bound. So if communication were free, how fast would this run? It would run at the speed of the local matrix multiply. So let me just use that as an upper bound. And so this is the fraction of peak, in the sense where peak is local matrix multiply. So all of these are little fractions less than 1. And let's just look at the trends and see if they sort of correspond to our mental model. So if I fix the problem size, n, so let's say I fix it at 2,000, and I increase the number of processors, the efficiency goes from high to, well, lower, but still decent. Why is that? If I use more and more processors on the same size problem, I'm spending more of my time communicating. So the efficiency does decrease, and you kind of expect that, but it's still okay. It's still better than a half. Now, let's suppose I fix the number of processors and raise the problem size, so increase n. I move from left to right. So now the efficiency gets higher. It goes up monotonically. And that fits our model too, because as n grows, I'm spending more and more of my time computing and less communicating. So if I go back to this formula, so this n cubed over p term benefits as n grows more than this term does, which is n squared over root p. So they have slightly different asymptotics. And so big problems on few processors is how you get to the highest efficiency. But of course, sometimes you want to run small problems on lots of processors because we're in a hurry. So we do want to attain the lower bound and, in fact, do better than this. So the question is, how can we do better than this allegedly optimal algorithm? And the reason I called it optimal is it had a hidden assumption, which was that we were only allowed one copy of the data. And so that we only had n squared over root p. But let's suppose that the matrix is small enough, or I had so many processors, and each had its own memory, that I could afford to fit not just one copy of the data, but c copies of the data. So that, in fact, my local memory would not be n squared over p, it would be c, the number of copies, times n squared over p. All the theory still holds, the lower bound still works. So what happens to the lower bound? So I still have the square root of m in the denominator, but now that grows by a factor of the square root of c. So the number of words moved can be made smaller proportional to the square root of the number of copies of the data. What about the number of messages? It's still m to the 3 halves. And so now the number of messages is going to go down proportional to the 3 halves power of the number of copies of the data. That is a lower bound. And so the question is, and that's a good thing, right? So if I quadruple the number of copies of the data because I have the memory available, the words move will drop by a factor of 2, and the number of messages will drop by a factor of 8. That's a good thing. So the question is, can we attain it? Now, historically, there was this one special case known for the special case where you had exactly the cube root of the number of processors copies of your data. That was just sort of a simple special case of all this. And we call that the three-dimensional algorithm because the way people visualized it was instead of taking your p processors and arranging them in a two-dimensional grid, a square root of p by square root of p grid of processors, they arranged them in a cube. And it was a cube root of p by cube root of p by cube root of p grid of processors. That's how they sort of thought about them. And each processor was responsible for doing one matrix multiply. One matrix multiply of an n divided by cube root of p by n divided by cube root of p submatrix. So everybody did one submatrix, one multiply, and then they just did a reduction to get the answer. And the trouble is that, this was a clever idea, but you don't always have that many copies available. It was sort of a very special case. So it turns out that there's a new algorithm that works no matter how much memory you have, that hits the lower bound for all possible numbers of copies, all the way from one copy, the original algorithm, up to the cube root of p. And it turns out that's a limit. You can't use more than the cube root of p copies. There's a sort of a theoretical limit. And I'll just show you the algorithm without the details of all the loops on 2 slides. So what we're going to do is arrange our p processors in this 2.5-dimensional grid. So it's a p over root c by p over root c by c grid of processors. So for example, if I had 32 processors, that would be a 4 by 4 by 2 grid of processors. That's how I'm going to arrange it. Originally, my data is just going to live on the top layer. So my matrices A and B are all kind of spread out in a 2-dimensional layout on the top layer of processors. So what does the algorithm do? So initially, let me number the processors by their coordinates, I by j by k. So there's processor ij0, that's the top row. It's going to own each of these processors is going to own a square submatrix, and that submatrix is going to be c times as big. So there's where I'm going to use the extra memory. So it's a 3-step algorithm. At the first step, each of these processors broadcasts its copies of A and B down. So every column of C processors is going to redundantly own A and B. Then each layer here is going to run the summa algorithm. It's going to run 1/7 of the summa algorithm. So in this case, it would run 1/2 of the summa algorithm. And it's going to compute half of all the partial sums you need in your matrix multiply. And so when I'm done, I'm going to have half the partial sums on each layer, and then I do a reduction. I do a vertical sum, and out pops the answer at the top. And if you do all of the counting, which I won't do, it hits the lower bound. So I'm almost done. Let me just tell you how good this is. It scales perfectly. You don't see communication at all, in a certain sense. So the thing is, as P increases, every time you add a processor, you get more memory. So in fact, if I can run my problem on P processors and I double the number of processors, the total amount of memory also doubles. And so C increases proportionally to P. And so the number of flops, the number of words, everything, they all decrease proportionally to p. It scales perfectly. I don't notice any slowdown when I increase the number of processors. And so here's a plot to kind of prove it. Here is the fraction of peak for a fixed problem size as I grow the number of processors, and it's dead flat. It doesn't get less efficient as you get larger. The classical algorithm gets less efficient. So here's kind of an extreme case. It goes 12 times faster than the classical algorithm. So this is for a relatively small matrix. It's an 8,000 by 8,000 matrix and a much bigger matrix, 128 by 128. And I'm comparing, as a fraction of peak, the new algorithm compared to the old algorithm where we had one copy. And it turns out 16 copies was the best thing to do. Here it was 12 times faster. And here it was 2.7 times faster. So we can ask ourselves, where did the time go? And this is the same data. I'm almost done here. So here's the two-dimensional algorithm with one copy of the data. Here's the 16 copy of the data. And it's broken down into communication time is red, idle time, waiting for neighbors is blue, and arithmetic is green. So 95% of the communication went away. And that's where all of that went. And here, all the communication went away too, but it was only about a third of the time, so the speed up wasn't as dramatic as it was over here. So next time, we will continue about what the impact is of this sort of perfect scaling.
Why did the computation become faster?
So the question is, how come the green bar went down? And that's because when we replicate the data, we have larger local matrices in each processor. So the local calls to matrix multiply went faster because they were operating on larger submatrices.